It is Sunday, the 14th of April 2019, and since you're here, you're probably wondering what's been going on in the artificial intelligence department lately, so here's an update. In the past, I focused the development of the project on back-end functionality, starting with the first designs of a genotype representation, mutating them into certain topologies, constructing phenotypes. You can see all of that in previous videos. Many things involved a lot of trial and error type of programming. Finding suitable activation functions and crossover operators, for example, was hardly more than a guessing game. The purpose of it all was mainly experimentation and debugging. With the backend being halfway functional now, it's time to introduce some actual usability into the system. In this video, I want to demonstrate the first iteration of the ongoing development. I'd like to begin with a little overview of the current architecture from a conceptual perspective. The heart of the program is the genotype class and all associated subclasses. The first drafts for this are from 2 years ago, but even though the visualization has undergone minor modifications, essentially it's pretty much the same thing. The genotype encodes the topology of a neural network in the form of chromosome objects and allows the application of evolutionary operators. On the other side, we have the network classes. A network consists of nodes and connections and provides basic functionality for signal processing. In order to convert these two, there is the converter class, which provides a transformation algorithm that turns a genotype into a functional network. Additionally, the converter receives interface information so that certain nodes in the network can be identified as input or output. Finally, the class that brings everything together is the phenotype class. The phenotype holds instances of genotype, converter, and the associated interface. Whenever the underlying genotype is modified, a new network is generated, which can then be used for signal processing. On top of all of that, there is a control layer called breeder. It handles so-called controllers, which are used to create, destroy, and manipulate all objects that will be used during the evolution process. The main controller is called master, and its only purpose is the management of more specialized controllers. Currently, the only controller the master is able to spawn is the creature controller. As the name suggests, it helps me to manage all creatures that exist during runtime. A creature is basically a wrapper for a phenotype object, but contains more information about it, such as name, generation, ancestry, measured fitness, etc. It also distributes update calls so that a creature's network is only updated if it's relevant at the time. Finally, there's the model layer with the proxy model at its top, along with all the various satellite models. Because many tasks in the backend can be time-consuming, I wanted the heavy lifting to be decoupled from the user interface. Each model is responsible for acquiring or processing data that will be displayed in the UI. The proxy model's only job is to synchronize between the UI models and the backend. Some of the models that are currently implemented are the image model, which handles the generation of preview images, the chromosome model, which does the layouting of chromosome information of a particular genotype, and the network model, which does the same for the network layout. The creature model handles everything that involves the management of all creatures or the modification of a particular one. Now let's take a look at the user interface. Most of what you see on the left is either connected to the creature or the image model. The new button creates a new creature with an empty genotype. It also assigns a generic name. Because the IDs are shared with other internal components, it doesn't start counting at 1, so don't let that confuse you. Clicking on one of the present creatures will select it and display its genotype, network, and interface. Currently, the interface for all creatures is hardwired to 2 input nodes and 1 output node. An empty genotype translates to a single hidden node, which is what you see on the right. As usual, every connection has a weight assigned to it. The absolute value of that weight is illustrated using different stroke sizes, but since the values are always hovering between -1 and 1, you're not going to see a lot of variation here. The color of a connection is calculated using a color map. As input, the product of the signal output multiplied by the outgoing connection's weight is used. A signal close to 0 appears as gray. Positive or negative signals are represented using amber or cyan, respectively. This color scheme is applied throughout the whole application. Both input and output interface are represented using slider elements and connect directly to the network model. The currently set input value are shown to the left of the sliders, as well as color mapped in the network's visualization. Theoretically, any value can be sent into the network. However, since I want to keep the values in a civilized range, I scaled the slider's scrolling area to the interval -1 and 1. The exit interface is implemented similarly, except that the output node signal is sent through the hyperbolic tangent function before being mapped to the slider. The value that you see on the left is the actual non-modified raw value. If needed, both input and output can be any real number. The signal value of a hidden node is visualized using these little indicators. The direction of the indicator shows the strength of the applied transfer function and is pretty much just another design parameter similar to a connection's weight. By clicking on Mutate, a sequence of mutations is applied to the genotype of the currently selected creature. There are different types of mutators that can be used for this task, as I showed in previous videos. The one that I use here is a layered mutator with fixed parameters, which means it will always produce a layered network with 4 layers and 3 nodes per layer. Other parameters like the type of mutation or the connection weights are randomized. The genotype of the selected creature is visualized in the center. By applying mutations, you can see how the genotype gradually grows until it eventually forms the desired 4-layer network. After every mutation or any other modification of the genotype, a preview image is generated off-screen by the image model, which is then presented in the creature list. As the network grows larger, I'm probably going to replace this by something else, but for now it should be accurate enough to help identify genetically related genotypes in future versions of the application. Any changes applied to the input interface are propagated throughout the network. I set the backend to operate on an update frequency of 10 Hz, which means it takes a moment until the output node stabilizes. If I move the sliders quickly, you can actually see how the input propagates through each layer. Once again, I'd like to point out that the user interface has no concept of layers. That's why the representation doesn't really look like a layered network. However, if you look closer, you can see that there is always 3 nodes clustered together, each group representing 1 layer. So the signal flow starts at the top and then goes counterclockwise until it reaches the output. Because this type of network has no backlinks, it always converges after 5 update calls, which takes roughly half a second. The remaining 2 buttons should be self-explanatory. In the next version, when the population controller is ready, I'm going to have another list here showing the currently present populations. Thanks to a consistent backend, I will be able to share creatures among multiple populations. If I delete the creature in this list, it would automatically remove itself from all populations. From here on out, there is a bunch of development directions and features I have on my list. One thing that I think always shows promising properties is to demonstrate that a neural network is capable of producing the most basic logical operators like Boolean gates. I'm pretty sure it can do that, but I want to include a demonstration nonetheless. Another thing that's been bothering me is that currently the mutator is hard-coded, so whenever I want to try another one, I have to dig into the code. Some additional parameters in the UI certainly wouldn't hurt here. The next big goal, of course, is to actually measure how the algorithm behave with regard to evolution. This includes the development of a population controller, UI elements, and fitness function evaluation. I'll start slowly by evolving simple solutions like producing a constant value, a flip-flop, wave functions, etc. and then we will see what happens. Like and subscribe if you're interested in this type of content, and I'll try to keep all AI enthusiasts in the loop. Thanks for watching, have a good day.